All right, so today I am going to introduce you to a laboratory technique called a titration. And our particular titrations that we're going to apply this to are acids and bases. And it is, a titration is essentially a technique that allows us to determine the concentration of an unknown solution very accurately, all right? In all titrations, we're going to have some acid neutralizing with a base. And we know from the last lesson that we're going to end up with water and a salt. But the key to it is that we will have a particular volume. Usually we're titrating the base into the acid, but we'll have a particular volume, let's say 15 milliliters. We will know the concentration of the base, let's say 0.50 moles per liter. And the question will be, what is the concentration of the acid? And we've already done questions like this, and we will know we will have a particular volume of the acid. And we've already done questions like this, where we take that 15 milliliters and convert it into moles of the acid, and then take the V and the N and figure out what the concentration is. So the calculations are something you've already done. We've done them a couple of different times when we first did some titrations, and when we first did solutions, we looked at this, all right? So the calculations you already know how to do. So today's lesson is on the technique of the titration itself, how we use it and why it is so powerful. Okay, so acid-base titrations, and this again is just a little discussion about what it is. A titration is a very accurate and precise laboratory technique to determine the concentration of a substance in a solution. So it's an analytical technique to find an unknown concentration. In a titration, a standard solution is titrated against a solution of unknown concentration. The concentration of the unknown is then determined by stoichiometry. When we talked about solutions and we talked about making solutions, I put a definition up there called a standard solution. It's usually formed by a solid, but it doesn't necessarily have to be formed by a solid. It can be a diluted solution. And a standard solution is simply a solution that the concentration has been determined very accurately. So it's very precisely known, many significant digits when it comes to the concentration. We're going to react that then with another solution we don't know the concentration of. One is a base and the other one is an acid. And then through some mathematics, we should be able to figure out what the concentration of the known solution is. So we use stoichiometry. Some equipment that goes along with a titration. Number one, we've got this tall, specialized graduated cylinder, and that's called a burette. And here I've got the burette, I've got it inverted with the little tap open, and as you can see, the name of that tap is called a stopcock. And if you want to giggle, you can giggle now if you'd like. All right, no gigglers. I'm usually the one who giggles at that. Anyway, that little tap is called a stopcock, and it opens and closes to let the liquid out. When you store a burette, because we will be using it for a couple of days, you always store it inverted with the stopcock open so that any liquid that's in the tip can drain out. And we'll look at that. We'll look at that a little closer. Again, you can see there's many graduations in this particular device, and it goes from 0 up to 50. Actually, I'll invert it and get it into the proper orientation. So we can put 50 mils in here. It starts at 0, and as it drains, we read how much of that liquid we've added to the well, in this case, an Erlenmeyer flask, all right? So we've got 3 Erlenmeyer flasks here in this case, and as we're titrating, you put that Erlenmeyer flask in there. You actually want that tip to be inside, and you're manipulating the little tap, and you're swirling, and you're taking a look at what that reading is, and you're kind of doing 3 or 4 things at the same time. It's kind of a neat little technique, all right? So the burette contains the standard solution, the one that you know very well. The Erlenmeyer flask contains the solution you don't know. And we essentially add an indicator. In this case, we're going to add phenolphthalein. And when we end up with a neutralized solution, the indicator will change color and will stop. And that'll tell us that we've added the same amount of acid and base. And that's an important part of a titration. Let me just jump ahead to the next slide here. We want to neutralize the acid with the base. And we want to stop right when we get to that neutralization point. We call it the neutralization point. And at that point, the number of moles of acid and the number of moles of base that we've mixed together in that Erlenmeyer flask are exactly the same. And we want to stop right at that point. And if we can stop right at that point, then we can take our volume of base that we know, our concentration of base that we know, we can figure out the moles, and because the moles are equal right there through the mole ratio, we can figure out the moles of the acid. And if we know the volume, we can get the concentration. When the indicator changes color, in this case, it's going to go from a colorless, because we're going to start with an acid in the Erlenmeyer flask, and it turns to that pink color. When the indicator changes color, we call it the end point. And that's when we stop. We stop titrating at the end point. Okay? The reason it's so accurate has to do with the size of this burette. It's a very small diameter, and so for every little drop, we can measure that change in volume very accurately. All right? We actually can titrate this. If we do a good job, we can get it to change color in one drop, maybe even a half a drop if we're really good at it. Now, in a moment, I'm going to set up the equipment. I'm going to show you how we do a titration, and we'll write some numbers down, and we'll gather some numbers up, and then we'll do some calculations. Tomorrow, you're going to do a titration where you're going to standardize some sodium hydroxide. So we're going to have some sodium hydroxide that we don't know the concentration to very well, and you're going to do a procedure so that you can learn the concentration and calculate the concentration very well. That's day one of our lab. Day two, we're going to take that sodium hydroxide that we now have standardized and made and calculated its concentration very well, and we're going to titrate that against some vinegar to see if the vinegar companies are actually putting 5% vinegar in their vinegar containers. We're going to actually be able to titrate and figure out the concentration of the vinegar and compare it to that. Just again to stress, you don't have to do a titration just with acids and bases. Any chemical reaction that will change color so that you can visually determine when you've got a certain ratio of moles can be used as a titration. In university, we use a chemical called potassium permanganate. We have it. We could make a solution of it. And we did something called a redox reaction. It has nothing to do with acids and bases. But potassium permanganate is a very purple color. And as you mix it with the thing that it's reacting, once you get to the point where the moles are equal, that purple disappears. And it goes from being very purple, within a drop or two, disappears. So we could use the same technique, except it had nothing to do with acids and bases. So it doesn't matter, it doesn't have to be acids and bases. We sometimes, as young chemists, associate the word titration with just acids and bases, but it can be with other chemicals. All right, so I'm going to show you how to use this. Actually, I'll point out one other thing before we get going. This, I don't know whether it'll function. This particular burette image is actually an animated GIF file. And the eyeball sometimes blinks. I don't know if we'll see it when it's recording. Oh yeah, no, it should have blinked by now. Because there we've got the scientist eye right at the meniscus. Yeah, it must be that when I'm recording I can't see the blinking. That's too bad. Okay. Oh, did he just blink? I think he might have just blinked. So I was going to show a video. Yeah, he blinks when I bring the screen up. I was going to show a video, but I'm actually going to demonstrate it. Now, in the past, I've done these questions first, but what I want to do is I want to jump ahead to the demonstration titration, and then we will come back and do those example problems. Okay. We're going to be doing the titrations in this room, and that's because we don't need Bunsen burners or anything like that. So we'll have the equipment set out there. What I'm going to ask you to do when you do grab your equipment is you're going to grab 3 100 milliliter beakers and probably 1 400 milliliter beaker, and I'll explain why you need all these. And then hopefully you'll be able to grab 3 Erlenmeyer flasks. There might not be enough Erlenmeyer flasks, so you might only have to work with 2, and then you'd have to dump them and then reload and do the titration 2 more times, because you sometimes have to do 4 titrations. I will be writing all this information down on the whiteboard or the chalkboard so that you can quickly take a glance, and all the glassware is up in the cupboard. It's very easy to grab it. I'll have Sharpie markers out there as well, and the reason why you have to have Sharpie markers is because you've got to label your beaker's base and acid and water, all right? And the extra one that you're going to grab is a waste container. In other words, you're going to put just some stuff that you use as cleaning agents, just kind of put it in there. It's essentially the same as having a sink nearby because we don't have sinks on our lab benches here. So you'll have a waste container, and I'll put that by the sink. Some other equipment that you're going to need is a pipette, and I think I've already introduced you guys to the pipette. It's a glorified straw, and I'll show you how that's going to function. And you will also need the indicator, some phenolphthalein. Let's talk about preparing the burette. First, let me grab some of my acid and some base. Here's hydrochloric acid. We're not going to be using hydrochloric acid, but this is just the one that I have grabbed to do the demonstration. And then we obviously need some base. And you need about 100 mils of the base. You might have to go back and get some more with a 100 mil beaker. So put it up to about 80 so that it's not like super full, but that's not too bad. Okay. And in this case, we're going to assume we know the concentration of the sodium hydroxide, and the concentration of my sodium hydroxide today is 0.50 moles per liter. All right? And we're going to pretend we don't know the concentration of the acid, but in actual fact, for my demonstration, the concentration of the acid is about the same. Preparing the burette. We need the interior of this device to be coated with the same material that we want to titrate. So we want to make sure that we don't affect the concentration of the base that we know to be 0.5 molar. So with the little tap closed, I take the base, and using the lip of that beaker, I just carefully pour in about 20 mils. Now notice I'm keeping an eye there. I'm not looking down, and that's about 20 mils, 15 mils. That's good enough. And so at this point, what you need to do is open the tap, let a little bit run through, all right? Close the tap. The other thing you need to do with your waste container, with the mouth of the burette over the waste container, rotate the burette and allow the liquid to flow out. So I'm coating the inside with the base. If there was some foreign chemicals in there, we're hoping that they're getting washed out with the base. And because I'm using base, when I refill, I'm not going to be diluting it if I had water in here. If I had water in here, then I would dilute the base, and I wouldn't know its concentration anymore. I do that 3 times, about 15, 20 mils, doesn't matter. Again, let it come to the end, rotate, 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 let that go in there. I didn't let any go through the tip this time. I should maybe do that. So put a little bit in here, number 3. Run some through the tip, right? Close that, rotate, rotate, and open the tap so that the liquid can drain out of the tip. All right, close. So that's a cleaned burette. I'm going to move that. We don't want it in that way. We can put that back into what we call the burette clamp. It just works like that. All right, you'll need it about that high. So we've cleaned the burette. Now we're going to load it. We don't need a funnel. All we have to do is very carefully put that lip of the beaker right into the opening, and the liquid will stick to the glass and travel down. And I'm keeping an eye on the top, and I can see the level rising. I don't need to get too worried about it. And I'm actually going to load it way past the 0 mark, right? So I've loaded it quite a bit past the 0. The reason for that is right now the tip is empty. If I were to start titrating, some liquid would flow through the tip, but no liquid would come out of the end. It means that I would measure some liquid, but nothing would have come out the end, and that would be an error. It means that, well, that'd be a mistake because you didn't fill the tip. It means that you would think that you measured some, but you didn't, and that would have a great effect on what our concentration is. And it's all about being very precise. So, back into my base beaker, which is fine because it shouldn't be contaminated at this point because I've cleaned it 3 times. What I do now is I open the tip wide open and I give it a little tap. There's some bubbles left, and there, all the last bubbles came out. Could you see the bubbles kind of shooting out there? If you're in the front, you could see the bubbles maybe. Now that's full. I'm still above my 0 mark, which is good because I want to start at a 0 volume. So now I'm going to just manipulate the tap. I know I've got my beaker in a good position. I'm going to keep an eye on that level, and I'm not going to open it right completely, but I'm just going to open it to where a little bit comes out. So I'm just controlling it there. I can see it coming down, and I can see the bottom of that meniscus, and I'm getting right to my line, and I stop right there. Bottom meniscus perfectly on 0. I'm going to take this and touch the side so that any liquid that's on the outside of that tip isn't hanging on the outside. And now the burette is ready to go. All right? The second thing you have to do, and this is going to be more for the second experiment, not the first one, and that is to prepare the pipette. In tomorrow's experiment, we're actually going to be titrating with a solid. So we'll be measuring out a little bit of solid in here. The acid is actually a solid acid. We're going to dissolve it and react it. But in the next day's experiment, we're going to be reacting it with vinegar. So I need to prepare the pipette in the same fashion in which I've prepared the burette. I'm going to draw the liquid up. I'm going to pop that off and put my finger on it very quickly. I bring it to my waste container. In this case, I do have a sink. And I rotate it, and I let the liquid come out the end. And I rotate it and let the liquid come out the end there. And I'm going to do a triple rinse with that as well. And I'm only going to do this twice because it's just a demonstration. Draw it up. Put your index finger on it. All right. Rotate that. Let the liquid come out the end. And just let that final bit of liquid come out. Okay. Now, I don't know if you can see it. Those up front can see it. But there's a little bit of liquid that stays in the tip. And these devices are designed for that. So don't try to push that liquid out. That's exactly what it has to be. So this is a 10 milliliter. And I want 10 milliliters of the acid put into the Erlenmeyer flasks. So Erlenmeyer flask in position. I draw up the liquid. I'm going to draw it up past the graduation mark, which is right there. Keep drawing. Ah, look at that. I ran out of, this pump is too small. So I got to actually bring it down. I'll make sure we got larger pipette pumps. This is actually a 5 mil pipette pump. Okay, so I draw it up past, flip it off, index finger on, middle finger and thumb hanging on. And it's okay if that tip gently sits on the bottom. At this point, I bring it up to eye level, and I rotate it with my thumb and middle finger, and I very carefully take the pressure off of my index finger. Very carefully. Very carefully, get it down to the spot. Come on, a little bit more, you turkey. Right there. So, finger on tight. Slide it up the side so no drips stick. Straight into there. Let it go. 10 milliliters. Transfer it. You got to wait for this. There's no speeding that up. Again, when the last drip comes off, touch the side of the glass. That one's done. I'm only going to do 2 titrations. You guys are going to be doing about 4 of them, but I'm only going to be doing 2. 2 titrations for you today just to keep things moving and let you work, right? Because I've already lost Jenna R. She's snoozing. I'm surprised I'm not hearing any snoring coming from her. She's completely out. Okay, again, past the graduation line, pop it off, put my index finger on, bring it up to eye level. It's okay if it touches a little bit on the bottom. Rotate that finger, and oh, this guy's a real pain. He doesn't want to come out. Sometimes you can control it. Oh, see what I just did there? Went past the graduation mark. No good. Got to draw a little more in. Oh, and that's really close to graduation mark. All right. Okay. Drop the side. In. There you go. If you have extra acid left, especially on the second day, actually I'll get you to do the same even on the first day, save it. Because in the end, we actually clean the burette with some acid. The sodium hydroxide gets sticky in there. So I leave that little bit in the tip, and I've got 2. You'll have water in your little water container. At this point, we know that we have 10 milliliters of our acid in each of those samples. It's been measured, and it's in there. We want to be able to swirl this so that we can see the reaction happening with the color. We've got 10 milliliters. We know that. So we can add some water, and it doesn't matter how much. I'm just pouring in about 20 mils. So we can add some water. I'll have to get a little more, so that we've got more water that we can swirl. Because the whole idea is mixing this so that we can see the color change. Add your phenolphthalein, 2 or 3 drops, doesn't really matter. I got 4 drops there, doesn't matter. 2 or 3 drops, 4 drops, whatever. Going to add a little bit of water here so that I'm ready for when I need the water. Put that right there. And now we're ready to titrate, all right? I've got the indicator in there. As soon as it becomes basic, it'll become pink. And I've got enough water that I can swirl. My first reading is the easiest reading. My first reading of my first titration is 0. Now, it's not just 0. It's 0.00 milliliters. Because we can estimate that fraction of a milliliter. You should always have 2 decimal places when you are doing a titration. If in your data you're missing 2 decimal places, I'll take significant digit marks away. I'll take communication marks away. We can measure it that accurately. Okay, so now I'm ready to titrate. You always want the tip to be below the Erlenmeyer flask, because if you were doing it yourself, if you've got the tip above, as you're looking, you could inadvertently take it out from underneath. If it doesn't land in the Erlenmeyer flask, the titration's no good. You've got to start all over again, because now we want everything that we have measured going into there. It's all about accurate measurement. I know that these 2 concentrations are about the same, which means I'm going to get a neutralization of about 10 milliliters, all right? At first, the color isn't going to do anything, but you guys did a little activity at the beginning where you kept adding it. What you did there where you added and stirred, remember how the color came and then it would disappear? You did a titration, but you did a really inaccurate titration. It wasn't using the proper equipment, but it was just to see what happens to the pH as you titrate. Does anybody remember what happened to the pH numbers as you kept adding base? What did they do? What happened to those pH numbers? Yep. They went up, but they went up really slowly. Remember how you thought, hey, is this what's supposed to be happening? Why isn't it going up? And then when you got to like 9 milliliters and then 10 milliliters, what happened to the pH? It skyrocketed up to 11. And that's the neat thing about a neutralization. Until all of that acid is completely gone, it's still acidic. So it stays fairly level until you get to that neutralization, then the pH rockets up. That's why this is also a very good technique. We add the base, it neutralizes, we add the base, there's still excess acid, and then when we get to exactly where it's the same, that pH shoots up. That's what gives it so much accuracy. Okay, so now we're ready to titrate. I'm going to bring this up a little bit. Students like one person to run the tap, and then the other one swirls. In a university lab, you're working alone, so this is the way it looks when you're working alone. Swirling and adding. And because I know it's going to be about 10 mils, I don't need to get too excited. Can we see the purple? Is there any purple? All right, what's going on here? I had the same the other day. I have I've got the graduation pointing the wrong way. I'm at 6. All right, okay. I would like to see some more purple in there. You'll notice I put a piece of white paper underneath it. I'm questioning my phenolphthalein because last time, and I'm right at 10, it hasn't hardly turned purple at all. Is there any purple getting in there? This is a failed titration. Well, that's craziness. Garbage. Waste of time. I got to get new phenolphthalein. Yep, I'll be right back. It's crazy. It happened on Friday as well, and I thought it was my solution concentration. I'll be right back. All right, right from the jar. I need a dropper. Actually, I could use that water dropper. Okay, which one was I mixing? This one? If it is actually basic, which it should be because I'm way past 10, and my phenolphthalein was no good, then this should indicate base, which means we should get very purple. Oh, look at there. There's our purple. Yeah, the phenolphthalein was no good. That's a failed titration, by the way, folks. Phenolphthalein right there. The extra back. That's no good. I've gone too far. That's too dark. A good titration should be just a hint of that pink. Just a hint. Because we don't want to be in that 11 spot. We want to be right at that 7. And it just starts to turn pink a little bit at the 7. No good. Failure. So I have a number there, but it's useless. So let me tell you what the current number is. So we'll start another titration, and this can happen. So paper in behind here, we are at 13.35. Getting rid of these. Oh yeah, it's great, isn't it? 13.35. That is my new value. Let's try again. And very often titrations will be no good. You've got to reload and do it again. I might have to reload one more. Okay, so now I'm going to titrate, and again, 13. I should be at about 23. So let's start adding. There you can see the pink starting to hang around. See how the pink kind of hangs around and disappears? As I get closer, it hangs around longer. And at that point, you've got to be really patient. You've got to slow down how quickly you add it. Someone who titrates well is a very patient person. I'm not a good titrator, as you could probably imagine. Anyway, so let's keep adding. So there it's kind of hanging around. Oh, it's really hanging around now. Whoa, now it's really hanging around. All right. Ooh, baby. That's exciting. There you can see the drops. Uh-oh. Ooh, it's close. Now I'm going drop by drop, and that color hangs around really long, and at some point it just stays. And we want the drop in which it stays. So now I'm going to get a drop out. Whoops, there's 2 drops. Oh, no. Oh, what a catastrophic 2 drops. That's way too dark. 2 drops. I got 1 drop too extra from my patients. As you can tell, I'm a very patient person. Too dark. I would probably want to redo that one. Actually, it's okay. There is worse. Like this is darker than that one, right? So that's a better titration. But if I had been patient with that last drop, I would have been okay. So now I got to measure this. I got to turn a little bit here. I'm going to take my white paper, put it in behind, and I've got 22 point, and it's right on the mark. So it's 22.90. 22.90. So my final reading is 22.90. I'll do one more. We'll do one more titration. Once you've done your first one, it becomes easier because you have an idea on when to stop the next one. And you don't, you tend not to go over on it. Oh, why do I have this in my left hand? I am left-handed, but I prefer to manipulate the pipette with my right hand. Oh, success. Drop the stride. Put that in like that. Touch on the side. We're going to add some of the good phenolphthalein. Okay, there we go. I'm going to add some water so I can squish it. Not squish it, swish it. Swish it. Swirl it. That's good. Get that out of the way. Now, I do not need to reload. If I'm at 23, I'm going to be down at 33. I only have to reload if I'm going to go beyond 50. So now, my next initial reading is 22.90. So I'm not going to reload. I'm just going to keep titrating. So that way you can do a bunch of titrations in a row fairly quickly. So again, run it, swirl, swirl, swirl. I'm keeping an eye on the bottom there. I'm observing the purple as it persists, and there it's persisting pretty good. So now I go to drop by drop, and again I watch to see as it persists. It's disappearing quite quickly still, so we're doing okay. And at some point in time, it's going to hang around for quite a long time. There, we're getting close. Whoa, I'm living on the edge. Whoa, whew, that's exciting. So it still disappeared. So now I want to really slow down because I want those drops to come at a very slow rate, and this is where I lose it. This is where my patience. So I'm trying to open this. There we've got a partial drop coming out. There we go. So now we're doing slow drip, drip. Whoop, there was one. Whoa, it's exciting. Whoa, disappeared. Whoa, next one, next one. Stop. No. Here we go. Drop. Oh, drop, another drop. Another drop, he's crazy. Okay. Oh, yeah, that was too much. What the heck? And look, there's still some hanging out again, which is measured. Actually, it's not bad. Not bad. And if I want to clean that off, that's why you have the extra water. There's my water. And I can squirt that on the tip there. And oh, look at there. Now I've made it even worse. Yeah, that was out. It was measured. Oh, anyway, like I said, I'm not very patient. You guys are much better at this stuff than I am. So now I'm going to bring that up here so I can see it. I'm going to take my paper so I can read the meniscus. And I've got 32.95. 32.95. So 32.95. Okay, so that's my demonstration of it. Let's now complete the calculation. So once you've got some real data, you're going to subtract. So I need someone to take the 22.90 minus 13.35. Yep. 9.55 milliliters. Oh, don't put the milliliters in the table, folks. Milliliters goes in the heading. And how about this other one? Yep. 10.05. 10.05. Now that's significant. Like I'm a half a milliliter off. That's really a crappy job. You should get them to be like within, tenths of a milliliter if you do it right. Ideally, we do at least 3. We want 3 of them that are consistent. Normally, you end up throwing out the first one because you didn't know where the endpoint was, and you zoom right by it. So normally, you have to do 4. But for this case, I'm going to just do the calculation and continue with it. The average volume then is, well, what is the average? 9.55, 10.05 over 2. Sorry, what was it? 9.80. 9.80 milliliters is the average volume. Okay. Now let's do the calculation. I need to bring up the Smart Notebook program here because I don't have a blank page. So now our calculation is going to be like any stoichiometry problem that we've done. We'll write out the balanced chemical equation, we'll write the numbers that we have, right? And we'll solve for that unknown concentration. So Smart Notebook here, we'll just turn on this auto hide and get it out of the way. Get out of the way. And let's just start with our calculation. So in this one, we had HCl, and we're reacting it with NaOH. Regular balanced chemical equation, NaCl and H2O. Notice we have a 1-to-1 ratio of H's to OH's, so this is a 1-to-1 to 1-to-1. Not exciting. I'll leave these on. Got some chemicals still sitting there. Again, just like we have done in the past, this is 10.00 milliliters because I measured it with the pipette. It's very accurate. This guy as well, what was our average? 9.80 milliliters. We know the concentration of one of the solutions. I told you it's 0.50, but for the sake of significant digits, let's say that we had standardized it and we know it exactly to 3 significant digits, moles per liter. And over here, we're looking for C equals N over V. Moles through the mole ratio. And now we do it like any other calculation. The only thing that we had to put some effort into was finding the volume of the base. We then take the average, and then we do a regular calculation. So again, C equals N over V. What's the V? The volume of the acid is 10 milliliters. We could do this in milliliters with millimoles, right? Did we talk about that in this class a little bit? You could do it that way. Let's do it that way, just for the difference. So 10.00 milliliters, which means I'm going to need some millimoles up here. That's okay, because we're going to start with milliliters up here. Now to figure out the N, I have 9.80 milliliters of sodium hydroxide. I want to get rid of that liters. That's 0.500 moles per 1 liter. Using my map, I need the mole ratio. This is a 1-to-1. The 1 HCl that I want is on the bottom. I'll write it in. Some people are still getting that upside down. For the 1, wait a minute, I got that backwards. I want the HCl. The 1 NaOH that I have for the 1 HCl that I want. And I stop there, and I'm going to end up, in this case, get rid of the liters. I'm going to end up with millimoles. Millimole. Okay? And how many millimole do I have? Yep. 4.9. I need 3 significant digits. So I need 4.9 something. 4.90 is exactly on? Okay. because this is all about significant digits. This is all about experimental accuracy. So now I can go back up to here, 4.90 millimoles, whoops, not milliliters, millimoles, divided by 10.00. So I know this also to 3 significant digits. What do I get? Oh, that's just moving the decimal over once, isn't it, by dividing by 10? So what's that? 0.490 moles per liter. And there is our unknown concentration. And that's cool because I made both of these solutions and I tried to make them both 0.5 and they're both close. I don't really know whether that's 0.5. That's what your job tomorrow is going to be. How close to 0.5 is our sodium hydroxide so we can know it very well, and then we'll use it on the vinegar the next day. Okay. Let's do another example here. I'm going to jump ahead to the last example here. This again is very much like what we did just moments ago. So what I'm asking to do, I'm trying to just get this thing out of the way. Let's complete our table. So somebody did a titration, 0 down to 16.59, volume of HCl added. Well, that's an easy calculation, 16.59. My next titration went 32, sorry, from 16.59 to 32. How much did I add on the next one? Yep, what do you got there? 15.66. Again, look at that. That's not very good at all. Look at the difference. We're almost a milliliter difference. That's terrible. I must have did that. What's the last one? 17? Oh, I forgot to change the number. There's a screw up in here because this is light pink and I want it to be really close. 17 point what? Ah, excellent. So I fixed yours. What does yours say, 30.25? Yep, I'm doing the same because that's going to bring us to where I want to be. What do we have if it's 30? Oh, sorry. Yours is the 17. Good. I want yours to be the 32. So I've fixed this. I'm catching up. I fixed this because I didn't like the number that we had created for that. Now what do we get? Yeah, 15.75, and that's what we want. That's what I wanted to illustrate. 15.75. Okay. Because what I wanted to illustrate was, look at these two are fairly close. You're off by, 0.1. That's fabulous. The colors are light pink. That's good. Which data would you exclude? I would say we're not even going to include this number because it was like a practice run. We weren't sure where to stop. Here, you've got 2 of them. And actually, we usually want 3 that are really good. I would say do another titration and make sure you get 3 of them that are good. Okay, so let's solve this one. What's the average of the ones that we're going to keep? In other words, not keeping that guy. 15.66 plus 15.75 divided by 2. 15.71, and that is milliliters. Okay. So we titrated 10 milliliters, unknown potassium hydroxide, and we know 0.5402 hydrochloric acid. All right. Let's go ahead and solve it. Really? Why would you open a second one? You're a piece of junk. Let's just jump to this one. Oh, there you go. That's handy. Thanks. So let's do this calculation. What do we have? KOH, I think it was. HCl. Again, I've given you a nice easy one. It's a 1-to-1 ratio. That's going to get me KCl. And that's going to get me, water. Oh, Monday morning. 1-to-1, right? 1H to 1OH. What were our numbers? What was the HCl? The HCl was the one we actually did the measuring with this time. What was our average? Yeah, Amy? 71 milliliters. This is the one we know, 0.5. Does somebody have that in front of them? 402? 402 moles per liter. This guy was 10 milliliters, so we must have measured him with the burette or the pipette this time. And as for all titrations, we want to figure out the C equals N over V. That's what it's all about. Again, we can work in milliliters as long as we have millimoles. And the calculation is identical to the one that we just did, 15.71 milliliters times the concentration. I've got to get rid of the liter on the bottom. So that is 1 liter, 0.5402 moles on the top. Again, it's a 1-to-1. This time I have the HCl. So for every 1 HCl, for every 1 HCl, I have 1 KOH. And that'll get me a number of millimoles. Because again, the liters cancel the liters, and I'm left with millimoles. How many millimole? Yep. 8.49. And I actually can keep one more digit on this one because I have 4 in my concentration. 87. Oops, 87. And that is millimole. 8.487 millimole. And when you divide by 10, you move the decimal place over 1 to the left. 0.8487 moles per liter. Okay? All right? And that's how you do a titration calculation. I'm actually going to stop there. I know we've got 2 more examples, but you can go ahead and do them. In the examples that I have here, you'll notice in this case, I don't have you worrying about finding an average. In other words, I've told you the average. So in other words, this is just the stoichiometry version of it. And we just did 2 examples of those. They're the same. This one, be careful because we're doing barium hydroxide, which is BaOH2, and nitric acid is HNO3. So we're going to have a 2-to-1 ratio in there. Your mole ratio won't be 1-to-1. Ooh, that's the trick on that one. I think you can handle that. And back to number 1, again, that's a straightforward sodium hydroxide with acetic acid, right? So sodium hydroxide is NaOH, and acetic acid, remember, is CH3COOH, and I'll help you with this one. It is this H that swaps out, all right? You don't need to write that arrow, but what you end up with is NaCH3COO, that's sodium acetate, and water, all right? And then again, we've got the volume of the sodium hydroxide, the volume of the acetic acid, and in this case, I did write it second, what's the concentration of the acetic acid? That's your C equals N over V that you're solving right there. Okay? So the mathematics of a titration is easy. The mathematics is regular stoichiometry, find the concentration of. It's always the same every time. You can work in millimoles and milliliters every time. The act of doing a titration is different. Okay? It's the new thing. It's the thing we got to work on. Let me just stop this for a moment.